In today's video, we're going to introduce the concept of linear regression, or in other words, the line of best fit. A while back when we were studying variables, we talked about categorical variables and numerical variables. We also said that if we have two variables, let's say variable A and variable B, if we think variable A causes a change in variable B, then variable A is labeled the explanatory variable and variable B is labeled the response variable. So for example, one might think that the weight of a car might influence the miles per gallon the car gets. So the explanatory variable here is the weight of the car, and the response variable is miles per gallon. Sometimes we would like to visually display the relationship between two variables, like the weight of a car and the miles per gallon. And the way that we can display it is by using a scatter plot. Now, a scatter plot is best suited for numerical variables. So we need two numerical variables. It's not well suited for categorical variables. So things like weight of a car, miles per gallon, those are things we measure and they're numerical. But things like eye color or place of origin, those aren't well suited for a scatter plot. So we're going to focus on numerical variables and creating scatter plots for these numerical variables. We'll also talk about the strength of the relationship between those two variables. So below I have a scatter plot that shows the relationship between the percentage of students who graduated high school in all 3,083 U.S. counties in 2012, and the percent of residents who lived below the poverty line in 2012. Now, the poverty line in 2012 was an income level below $23,050 for a family of four. So let's take a look at this scatter plot. On the x-axis, we have percent of high school graduates. And notice the tick marks here. So 50 is 50%, 60%, 70%, 80%. And on the y-axis is the percent of people living in poverty. And our tick marks are 0, 20, 40. Now, there's about 3,000 counties in the US, and each one of these dots represents a county. And let's take a look at this county right here in the upper left-hand corner. So this is a county whose percent of residents who graduated high school is a little over 50, let's say 51%. And in that county, the percent that's living in poverty is above 40. Notice that these tick marks are units of 20, so this must be 50, so maybe it's about 46%. About 46% of people in that county are living in poverty, and about 51% of the students who go to high school graduate. Now, when we think there's a causal relationship between the two variables, we let the x-axis be the explanatory variable and the y-axis be the response variable. So here, the percentage of students who graduated high school influences, or we think influences, the percentage of residents living in poverty. Now, what kind of relationship do we have between the two variables? Looking at the scatter plot, you may notice a linear relationship. And this linear relationship, so it means it looks like a line, it also looks like it has negative slope. Recall that negative slope means when we look from the left to the right, the line is going downward. So it has a downward trend. So there appears to be a negative linear relationship between the two variables. In other words, the scatter plot suggests that as the percentage of high school graduates goes up, the percentage of people living in poverty goes down. How strong is this relationship? We want to quantify this, give this a number. So correlation is a mathematical way to describe the strength of a linear relationship. We use the letter R to represent correlation, and the value of R is always between 1 and -1. Let's take a look at the graphs at the bottom of this slide. Notice in the middle we have no correlation, or R is equal to 0. That means that there doesn't seem to be any association between the two variables. The further you go away from 0, and the closer you get to 1 or to -1, the scatter plot looks more like a line. So for example, let's look at the very left graph. When r is equal to 1, that means all the dots on the scatter plot line up in a perfect line. Now, if r is equal to 0.9, that means the dots are pretty close together. They're tightly bound together, but they're not exactly on a line. And then 0.5, you can see things are spreading out a little bit, but it does have a linear look to it. And so the closer you get to 0, the more spread out things are. And the closer you get to 1, the more things line up on a line. And if the value of r is positive, like this 0.5, 0.9, and 1, the slope of the line is positive, meaning as we look from left to right, the line is going up. Now, if r is equal to negative 0.5, that means we have a little bit of an association that kind of looks like a line, but a line with negative slope. So compare 0.5 to negative 0.5. They kind of have the same association. How things are spread out is kind of the same. It's just that one has a positive slope and one has a negative slope. With negative 0.9, the dots are closer together and we have a negative slope. And finally, when r is equal to negative 1, all of the dots line up on a perfect line and it has negative slope. I also want you to pay attention to the definition of correlation. It says it describes the strength of a linear relationship. So when we talk about correlation, we're always talking about lines. Here I have 4 different graphs, and what I want to know is which one has the strongest correlation. That means which one of these graphs has a value for r that's the closest to positive 1 or to negative 1. So we're going to go ahead and eliminate the first graph because this is not a line. This is kind of parabolic. It kind of has a U shape to it, and there's a strong association between the dots here, but it's not linear. So correlation does not apply to A. For B, C, and D, I would say B has the strongest correlation, and the value of R is positive because the slope is positive. D has a negative correlation, and C has what looks like to me a positive correlation. I would say of B, C, and D, C would have a positive R, but it would be close to 0, while D would have a negative R, but it would be somewhere between 0 and negative 1, and B would have a positive R, and its value is closer to 1 than D is to negative 1. So B has the strongest correlation. Right now, we're not really worried about the actual value of R. You would need a calculator or Microsoft Excel to find that for you. Right now, I just want you to get a feel for the correlation. So of the following 4 choices, which one best suits this graph? Which one is the correct correlation? Well, let's eliminate a few. First off, we can get rid of A and D. Both of those values are positive, and looking at this scatter plot, if we were to associate a line to that scatter plot, it would have a negative slope. And for a negative slope, the correlation needs to be negative. So A and D are not correct. B is also not correct because correlation is always a number between negative 1 and 1. And this number is past negative 1, so we can eliminate it, and we're left with C. The 2 scatter plots below show the relationship between final and mid-semester exam grades recorded during several years for a statistics course at a university. Based on these graphs, which of the 2 exams has the strongest correlation with the final exam grade? So take a minute, pause the video, and see which one of the graphs you think has the strongest correlation. Okay, I would say exam 2 has the strongest correlation with the final exam. The dots in the right scatter plot are closer together than in the left scatter plot. Can you think of a reason why the correlation between the exam you chose in Part A and the final exam is higher? Well, what I have found is usually during the first exam, students don't really know what to expect from the instructor. They're kind of new at the test-taking process for the particular course. And by exam 2, they have a better feel for what's going on in the course and how the instructor grades them. And that's why I think exam 2 would have a stronger correlation to the final exam than exam 1 would have. Let's go back to the scatter plot where we were looking at counties and the percent of high school graduates and the percent of people living in poverty. Our goal is to fit a line to this data. If you and I both try to make a line that represents this data, we may come up with different lines. For example, here are 3 different lines that one may say best fits this data: the blue line, the green dotted line, and the red dotted or red dashed line. What we would like to do is find the perfect line. There should be one line that best fits this data. We're going to talk about how to find it and what are the equations for the line, like what is the slope and what is the y-intercept. Let's do a quick review about lines. So remember that y is equal to mx plus b is the equation of a line, where b is the y-intercept and m is the slope. I'm going to show you a few lines, and we're going to look over them and see if we can find the slope and the y-intercept. Now this line, the red line on the right, goes through the origin, and the y-intercept is where we cross the y-axis and it crosses at 0. So that's why there's a plus 0 in the equation, and the slope is 2 over 5, which means we go up 2 and to the right 5. It's rise over run. So let's take a look at our graph. Notice that these tick marks are units of 2, 2, 4, 6, 8, 10, and 2, 4, 6, 8, 10. So to go up 2, there's 1 tick mark, and then to go to the right 5 is 2.5 tick marks. So 1, 2.5. Then go up 2 and to the right 2.5. 2 over 5 is the same thing as 4 over 10. So you could go up 2, 4, and to the right 2, 4, 6, 8, 10. The equation of this line is 3x plus 2. Notice that it crosses the y-axis at 2, and the slope is 3. The number 3 is the same thing as 3 divided by 1. So it's up 3 and to the right 1. So up 1, 2, 3 over 1. It goes past what we can see in the graph, but we could also go down 3, 1, 2, 3, and to the left 1. Let's do one more. The equation of this graph on the right is negative 1/6 x minus 1. So notice that we cross the y-axis at negative 1, and the slope is negative 1 over 6. The slope is negative, and so we can go up 1 and to the left 6, or from the y-intercept, we can go down 1 and to the right 6. And this is a model for this scatter plot, a line of best fit. And I made this red line to represent the equation of this line. And I made this red line here to represent that equation. Notice that I put a little hat on y, and x does not have a hat. X will be the percent of high school graduates in a county, and y will be the estimated percent of residents in a county living in poverty. So we have 3,000 counties, and there's a bunch of different dots, and not all of the dots live on the red line. So that's why we're putting y hat. Whatever we put in for x into this equation, it'll give us an estimate, and that will be something living on the red line. Let's look at the slope. It is negative 0.591. And this is rise over run, or the change in y over the change in x. Let's see if we can interpret the slope in context of this problem. So the negative 0.591 means we're going to go down 0.591 for every unit we go over to the right, because it's negative 0.591 over 1. So in context of the problem, every time we move one unit to the right, we go down 0.591. Remember that X is high school graduates. So for every 1% increase in high school graduates, we expect to go down or have a 0.591% decrease in people living in poverty. That's the Y variable. Now we create a line of best fit to make estimates. So for example, suppose 75% of a county's high school students graduated in 2012. What percent of residents do you expect lived in poverty in 2012 in that county? How would I use my line of best fit to give me that estimate? Well, since X is the percentage of high school students who graduated, and that's going to be 75, we're going to plug 75 into X for this equation. And if you simplify, you get 20.269. So we would expect about 20.3% of residents lived in poverty in 2012. I made a little red dot here so you can see where it lives on the line. Let's try another one. Suppose 90% of a county's high school students graduated in 2012. What percent of residents do you expect lived in poverty in 2012? So we put in the 90 into X, and we find Y, it's 11.4. So we expect about 11.4% of residents in that county lived in poverty. So the next thing I want to do is discuss how the computer came up with this model, this line of best fit. To do that, I need to define something called a residual. So a residual is the leftover variation in the data after accounting for the model fit. In other words, it's the data observed, so you're going to have a dot on the scatter plot. It's the Y value, the data observed, minus the Y value from the line, the data expected. In other words, it's the vertical distance from the dot to the line. We usually use the letter E to represent the residual. Now you can see in this equation I have EI because we may have a bunch of different dots. So if we call one dot the first dot, then its residual is E1. And we take Y1, which is the Y value of that particular dot, and subtract Y hat 1, which is the value on the line. And then we may have our second dot, so its residual is E2, and we subtract its Y value, which we call Y2, and the dot on the line, which is Y2. And I'll explain this more in our example. So here I've circled a dot. Suppose the dot circled is the 350th observation. So I can number every single one of these dots. We said there's 3,083 of them. I labeled this particular dot 350. I'm going to calculate its residual, which is its vertical distance from the line. And I'm going to call that E350. Now, let's take a look at where this dot is located. So its X value, if we look down here, is somewhere between 70 and 80. If this is 75, it's kind of close to 77, which is what I wrote here. It's located at 77, and the Y value is very close to 40. It turns out it's 39.2. Now this dot represents a county in the US with a 77% high school graduation rate and a 39.2% poverty rate. What is the residual for this observation? So what we're going to do is we're going to take that X value, the 77, and we're going to find the Y value that lives on the line corresponding to that X value. So we're just going to take the 77 and plug it into the line, and we get 19.1. So the residual is the Y value of the dot, 39.2, subtract this estimated Y value that lives on the line, the 19.1, and we get 20.1, which is the vertical distance from the dot to the line. Now you can pick whatever dot you like on this scatter plot, and if it lives above the line, that vertical distance is always going to be positive because the Y value of the dot is above the Y value on the line. If you subtract the two, you're going to get a positive number. If you pick a dot that lives on the line, for example, maybe one of these dots over here, it looks like there's a dot that lives on the line. If I took the Y value of the dot that lives on the line and subtract the Y value on the line, I would get a residual of 0. And then if I take any of these dots down here, like this one, and remember the formula, it says take this Y value and subtract the Y value on the line, the one directly above it. Well, then you're going to get a negative number. So if you live above the line, the residual is positive. If you live on the line, the residual is 0, and if you live below the line, the residual is negative. I've summarized this here. An observation living above the regression line just means the line of best fit, its residual is positive. If an observation is below the regression line, then its residual is negative. And if an observation is on the regression line, its residual is 0. The best linear model, which we call the line of best fit, is constructed in such a way that residuals are as small as possible. In other words, it is a line that minimizes the distance from all points in the scatter plot. I'm going to tell you how Microsoft Excel and Python and RStudio create this line of best fit. What's going on behind the scenes? We're not going to get into too many details. I'm just going to kind of give you a brief overview of that so you can have a little bit of an understanding. So let's take a look at the scatter plot. I've already drawn a line there, but notice how many dots I have. I have 1, 2, 3, 4, 5. Looks like I have 14 dots. And I want to make a line of best fit. To make a line of best fit, the equation of a line is mx plus b. If you can give me the m, the slope, and b, the y-intercept, if you can find the best values for these two, then you have given me the equation of the line. So that's what you need to find. And that's what Microsoft Excel, Python, RStudio, any other statistical software, they have to come up with an equation for m and for b. How do they do that? Well, they calculate residuals. So we want to minimize the residuals. That means every little dot that we have, we want to find the smallest distance. We want to move that line up and down so that every dot has the smallest distance from the line. So remember, to find the residual, you take the y value of the dot and find the y value that lives on the line and subtract the two. Remember that we have 14 different dots, so we'll have 14 different residuals. Let's take a look at this dot that I have with the little arrow. Think about what would happen if I move this line just a tiny bit up. Don't go past the dot, just a tiny bit up. Well, that residual, which is the vertical distance from that dot to the line, it would get smaller, so it would reduce that residual. But at the same time, there's a dot underneath it. And if you move that line up, the distance between that dot and the line gets bigger. So notice that by moving the line up and down, it may help some of the residuals, but hurt other residuals. So we need to figure out a way to move the line up and down or twist it to change the slope so that how it impacts all the residuals, overall, it makes all of them as small as possible. So we need a formula that incorporates all the residuals. Sometimes one residual might get bigger just by a hair, but it reduces the residuals for others. And so overall, it would be a better fit for this scatter plot. So the line of best fit will make all of the residuals as small as possible. How can we minimize all the residuals at the same time? Well, one idea is to minimize their sum. So for example, E1 plus E2 plus E3 and so on. So this is a good idea. It just turns out that because we can have negative residuals, like let's say, for example, this guy right here, his residual, let's say, is +1, and the one underneath, his residual is -1, let's just say. Well, they will cancel out each other. And we don't want to get a sum of 0 unless all the dots live on the line. So we need to fix the problem with getting negative residuals. So how we can do that is one way is we can put absolute value onto each one. And that way, all of the negatives and all of the positives, they don't counter each other. But there's a problem with absolute value. If you've taken a calculus course, you may remember that to minimize is the same thing as finding a derivative. And if you haven't taken a calculus course, that's fine too, just in case you have. To minimize a function, you need to find the derivative. And it's hard to find the derivative of absolute value. So what you do instead is you minimize the squares of each one of the residuals. So that's the idea behind it, and it's why it's called least squares regression. So Microsoft Excel figures out what way we can adjust this line so that this sum is minimized. Now, most of the time, if you're working with data, you can get the equation of the line of best fit from Microsoft Excel. But I would like to do this one time by hand, just so you get a feel for how it works. So we'll need to find the slope and the y-intercept. And the slope is the standard deviation of the y variable divided by the standard deviation of the x variable times the correlation. And the value for the y-intercept is you find the mean of the y variable, and then you subtract from it the slope times the mean for the x variable. A chimpanzee's diet mostly consists of fruits, seeds, leaves, flowers, and small insects. However, chimps are known to hunt small animals in groups. And if you have this PowerPoint slide, you can click on this link and you'll be sent to a research article where you can learn more about chimps and how they hunt in groups. So the size of a chimp's hunting party seems to be associated to the probability a hunt is successful. That makes sense, right? The more chimps we have working together, the more likely their hunt will be successful. So suppose we sample hunting groups of chimpanzees and calculate the probability of the group having a successful hunt. The data is given in the table and scatter plot on the next slide. So on the left, you see the data, the number of chimpanzees in a hunting party, and the percent of successful hunts. And on the right, you see a scatter plot where the x variable is the number of chimps, that's the explanatory variable, and the y variable is percent of successful hunts. So for example, when we have one chimp, the percent of successful hunts is 30%, and you can see that dot right here representing that information. So let's put this information into Microsoft Excel and see if we can find the standard deviation of y, the standard deviation of x, and the correlation coefficient. And that will give us m, and then we'll also see if we can find the average of y and the average of x to find b. I've also given you some of that information down here. Let's verify it as well. So I'm going to go and put this data into Microsoft Excel. Okay, so now I've put the information into Microsoft Excel. Row A is the size of the hunting party. Row B is the percentage of successful hunts. And down here at A10, I'm going to type equals average. And I'm going to highlight these cells. And I get 4.5. Then next to it, I'm going to find the average of these cells. And I get 56.125. So maybe write that down somewhere. It's going to show up on the slides in just a minute. Let's also find the standard deviation. So I'm going to type stdev dot s for sample. I'm going to put these cells, A1 through A8. That will give me the standard deviation of the hunting party. And now let's find the standard deviation of the successful hunts. So 2.4 and 13.8. So this is Sx and this is Sy. This is X bar and this is Y bar. So I'm going to make a scatter plot of this data. I'm going to go to Insert, Chart, XY scatter. And as you can see, these dots are pretty close to a straight line. Not exactly, but pretty close. So somewhere over here, I'm just going to go right here. I'm going to type equals correlation. So CORREL, and I'm going to stop and I'm going to put a parentheses. Now, what kind of correlation do we expect? We expect a positive number because this line has a positive slope. And I would think it would be kind of close to 1 because these are almost on a straight line. So I'm going to highlight A1 through A8, comma, B1 through B8. Parentheses. Zoom in a little bit so you can see that. And then I'm going to hit enter, and I got 0.96. That's really close to 1. So that's telling me that these dots are almost on a straight line. Now let's go back to the PowerPoint. Okay, so we have that X bar is 4.5, Y bar is 56.1. We got that information from Microsoft Excel. The correlation coefficient is 0.9629. The standard deviation of X is about 2.5, and the standard deviation of Y is about 13.8, and we verified this with Excel. Now let's plug all of that information into M and into B. So for M, we're going to take 13.8, divide by 2.5, and multiply by that correlation coefficient, 0.9629, and I got about 5.3. Let's interpret this slope. Remember, 5.3 is 5.3 over 1. 5.3 is the rise. The 1 is the run. So we go up 5.3 every time we go to the right 1. So for every 1 additional chimp in the hunting group, we expect an increase of about 5.3% in successful hunts. Let's find the equation of the least squares line. We need to find B. B is Y bar minus the slope times X bar. I got 32.25. And now that we have the M and the B, we just plug that into the equation of the line. Y hat is mx plus b. So y hat is 5.3x plus 32.25. So the next thing we want to do is we want to make a prediction. Now we have to be careful with predictions. We don't want to go too far outside of our data. So let's predict the percent of successful hunts for a group of 9 chimpanzees. Remember that X is the number of chimpanzees, so we're just going to plug in 9 into our equation, and we get 79.95. So there's about an 80% chance that a hunt will be successful if we have a group of 9 chimpanzees. What about this time if I give you the success rate? Can you find the number of chimpanzees in the group? So a group of chimps have a success rate of 91%. About how many chimpanzees would you expect to be in that group? This time we set y equal to 91 and we solve for x. I have to do a little algebra here, but you'll get 11.08. So about 11 chimpanzees.